We'll get the bot to review a paper. It's one of the images from a paper. And we will get the bot. And then we get the text-to-speech model to actually discuss, see if it's actually accurate or not. We had the tool to extract images and text from papers. It should be available on the website somewhere.
You're staring at your screen with that intense, I just found a neural network that can predict the perfect cup of coffee look. What esoteric paper has captured your data scientist's soul this morning?
It's a goldmine, Hosk. Afzal et al. 2025. They're using vision transformers, or VIT, to classify electrographic seizures from intracranial EEG, or IEEG, recordings, specifically from patients with the NeuroPace RNS system.
Wait, a vision transformer? Isn't that the technology that recognizes cats and decides if a hot dog is, in fact, a hot dog? You've turned someone's internal brainwaves into a meme identifier for epilepsy? That's beautifully absurd.
The signals are first converted into a time-frequency spectrogram, essentially turning raw brain data into an image. That's the key. The VIT is then trained on these images to distinguish seizure activity from non-seizure baseline. They hit 96.8% accuracy on the test set.
So the brain is speaking in code, and the VIT is translating the static into a high-res photograph of chaos. But why VIT? Why not a good old-fashioned convolutional neural network, a CNN? Are CNNs now considered old-fashioned, like flip phones?
Because of the self-attention mechanism. CNNs are great at local feature extraction, like spotting a very tight, defined squiggle. But seizures are dynamic events. They have long-range dependencies and require global contextual information across the entire time-frequency image.
Ah, the VIT has a better memory than the CNN. The CNN is the guy who says, this last 5 seconds looks bad. The VIT is the one who says, wait, I saw a subtle frequency shift 30 seconds ago, and I'm connecting it to this full-blown gamma burst now. It's a pattern. It's a data model with dramatic irony.
Precisely. It allows the model to dynamically weigh and relate information across all time points in the input sequence, which is critical for capturing the narrative of seizure dynamics. They prove this by outperforming both ResNet 50 and a standard 2D CNN baseline on the clinical validation data.
Okay, but how do we know the VIT isn't just a very confident guesser? This is where I need to see the receipts.
That's the best part, the explainability analysis. They used attention maps. When the VIT was highly confident in a seizure prediction, its attention was highly focused on specific high-frequency bands in the spectrogram, which is exactly what epileptologists look for in focal seizures.
So focused attention equals brain on fire.
And conversely, for non-seizure classifications, the attention was diffuse, spread out across the entire spectrogram. No single hotspot of chaos to focus on. It's essentially building a statistical profile of boredom.
That is the most relatable finding in all of deep learning. High-confidence seizure equals sharp, specific focus. Non-seizure baseline equals unfocused, scattered attention. I believe I have now fully personified a VIT attention map during my set breaks.
The real-world application here is massive, Hosk. Clinicians currently have to manually review thousands of hours of IEEG recordings. It's labor-intensive, costly, and prone to fatigue-related inconsistencies. This VIT model is a tool to filter, classify, and aid that review process efficiently.
It's the ultimate time saver. By turning complex brain electricity into a simple, classifiable image, they've built a scalable assistant. The vision transformer is now a highly specialized, non-fatigued, and extremely accurate secretary for the human brain. And for that, I raise my mug of coffee.
Cheers to the chaos being structured by algorithms.
Chaos, but with 95.8% accuracy. That's the dream.
Yes, when they're doing the score, you can see more of a difference between the good old ResNet, convolutional neural net, and the new model, whatever. I don't know, what is it, 86 million parameters? Hope not. I have to check. Yeah, the difference is not as visible when you just look at accuracy. Well, primarily because we are the ResNet already doing comparable results. Yeah, those would not be significantly lower, would they? The ResNet should be much more straightforward to run. Yeah, so we have an example of a seizure. Don't know why they're showing grayscale. Okay. Grayscale. Yeah, we ask the bot to review the figures as well. Let's see which figures it actually picks up on. I don't know if you can hear or if you can tell, but there is a human in the loop. If you have any questions, pop them in the chat. This paper just came out today. This is the reference. The reference using vision transformers for electrographic seizure classification to aid physician review of intracranial electroencephalography recordings. Did I pronounce it correctly? How many likes do I get for the pronunciation? So using the NeuroPace RNS, very specific system, so it would not be actually comparable to anything else. So if you want to replicate the results, you need that specific implant. I don't know what that bit there is. Don't remember seeing it before. I have an example of a seizure. Yeah, let's see what figures the robot.
Yogic, you need to stop thinking about a T-Rex scatter plot for a second and look at the actual images the vision transformer is analyzing. It's all in the figures.
I'm ready. Show me the brain selfie.
Let's start with the input data, figure 3 and 5. This is where the magic happens, the spectrogram. Figure 3A is a seizure. It's not a squiggly line. It's a heat map of brain activity over time with frequency on the y-axis. See that bright yellow red mass extending from about the 10-second mark?
Ah, the jet color map as mentioned in figure 5A. So the brain, when seizing, looks like a tiny, contained high-frequency fire. The VIT isn't reading data, it's reading a thermal image of a neural meltdown. And figure 3B, the non-seizure, that's just blue and green. The brain is clearly chilling out watching TV.
Exactly. The color is essential too. Figure 6 shows that models using color spectrograms, the jet color map, consistently performed better than those using simple grayscale inputs, figure 5B.
So, turning the brain's internal panic into a dramatic full-color movie poster actually improves the algorithm's performance. It's like the VIT needs the extra visual flair to know it's a serious event. Data needs drama.
And speaking of drama, look at figure 4. This addresses a real-world problem, stimulation artifacts. The RNS device records, but it also stimulates. Figure 4A shows that artifact, those vertical black lines contaminating the signal. Figure 4B shows the cleaned-up signal.
The VIT is so good. It can filter out the brain's own electrical feedback. It's like a stand-up comedian who can perform perfectly while simultaneously ignoring the sound engineer's faulty microphone. Figure 7 shows that removing the noise only gave a slight improvement. The VIT is robust. It's basically saying, I can see the T-Rex even through the static.
Now, let's jump to the results. Figure 8 is the big win. On the clinical validation set with unanimous expert agreement, the VIT-86M model, that's 86 million parameters, achieved a 95.6% accuracy and a 94.8% F1 score.
And it's spiking above ResNet 50 and the 2D-CNN like it's not even a contest. The vision transformer is definitively the smartest kid in the class, validating that converting brain signals into high-resolution images is the future.
To get granular, look at the confusion matrices in Figure 9. This is where we check for generalizability. The model was trained only on long episode recordings, but they tested it on magnet, scheduled, and saturation events.
Wait, you're saying they trained it on the long episode full-length movie, but it nailed the classification for the scheduled twice-daily quick check and the patient-triggered magnet swipes? Look at the scheduled matrix, bottom right. Out of 95 unanimously labeled non-seizures, it only misclassified 4. It showed strong performance across all categories. It generalized the pattern of chaos it learned from long-duration events to every other IEEG type.
Incredible. It learned the essence of the seizure. But my absolute favorite, the one that tells the VIT's story, is Figure 12. The attention maps.
The explainability section. When the model had a high confidence score for a seizure, e.g. 0.99 probability, the attention map shows the focus is tight, intense, and high frequency, a targeted yellow patch.
Focused attention. Warning, brain activity is evolving rapidly at 60 plus hertz. Classify as seizure.
And for the high-confidence non-seizure examples, e.g. 0.002 probability, the attention map is diffused and scattered, covering the whole image equally.
Diffused attention. Everything looks like everything else. No specific high-frequency fire. Classify as non-seizure.
The algorithm literally gets bored when there's not a seizure. The vision transformer has confirmed that a clear, focused mind is a dangerous mind.
It provides an interpretable, qualitative explanation for the model's binary output. It's science that shows its work.
And science that, visually, is absolutely terrified of high-frequency yellow rectangles. We should make that the BioniChaos logo.
Okay, not sure about that. We're not changing the logo. So we doing a critical review. Are there more figures? There are more figures. It's just examples. Yeah, obviously there will be a huge disclaimer. Is the dataset available? The original contributions presented in the study are included in the article supplementary material. Further inquiries can be directed to the corresponding author. The original contribution. It's a very odd way of... is the data available or not? The original contribution presented in the study are included in the article supplementary material. I assume supplementary material definitely would not include all the raw data, that's for sure. So essentially it's somehow a fancy way of saying the data is not available. I don't know what's in the supplementary material. Do we need to look at that? It surely will be some sort of very simplified metadata. There's a couple questions. So the question is the other models that they're comparing. That's the three experts, confusion matrix. Yes, this is the main result, figure 8. So the question is the ResNet 50 and the 2D-CNN, are they actually comparable models? Because they use them like out of the box. So let's actually... Okay, so we want to continue the critical review of the results in the paper. The main result, I guess, is figure 8. If there are any other major results, do let us know. But essentially, the three models, the ResNet 50 and the 2D-CNN, are probably just out of the box and they were not fine-tuned specifically for this dataset. I don't know, can we find what do you think? Or can we find any evidence for specific fine-tuning in the text? But essentially the suspect is that the VIT, whatever, the 86 million parameters, which is a crazy number by itself. We need to actually do like a parameter reduction. I don't know if it was done or not. to explain, how the model is actually doing the classification, the seizure, non-seizure. Also, they're just doing classification, right? They're not trying to do prediction, so just detection of seizures at this stage. Or did they mention prediction as well in the text of the paper? But essentially, I suspect the VIT, this highly performance model, was actually fine-tuned to this dataset, so that could be why it's doing so much better. Potentially, I don't know if it was tried or not, you could get the same results with a much simpler model, but that is fine-tuned to the specific dataset. And also another thing, if you can tell if the raw data for this to replicate the result is available or not. I suspect not. And yeah, everything we do eventually appears on BioniChaos.com. Go check the website, provide your feedback. It will make us very happy. Like this much happy. Some things don't fit on the page. So you need to kind of make it full screen. Then it kind of fits. Let me know if you want me to cover any of those other tools on the site, change them, improve them. Don't forget to smash that. What do you think that button is? It's 17.
Listen, let's take off the rose-colored glasses for a moment. This 96.8% accuracy is on the paper's own test set. I'm a comedian. I know when the house lights are dimmed to make the applause seem louder. Let's talk about the competition.
You're hitting the sore spot, the baselines. They compared their VIT 86M parameters to a ResNet 50, 23M parameters, and a relatively simple 2D CNN, 22M parameters.
That's not a fair fight. The Vision Transformer is the heavyweight champion, and they put it in the ring with a couple of underfed flyweights. Was the 2D CNN intentionally simplistic? They describe it as having only 3 conv 2D layers with basic pooling. You could build a better CNN in a graduate school lab.
They did also include a time series transformer and a 1D CNN for time series comparison. But again, the VIT is fundamentally more complex and powerful. The paper's strongest argument is not that VIT is better than the most optimized state-of-the-art CNN. It's that VIT, leveraging ImageNet pre-training on spectrogram images, offers a substantial performance boost over the models they chose to benchmark.
It's an architecture choice that favors their specific input, the image. They converted the raw signal to a time-frequency image using a jet color map, which Figure 6 shows is critical to the VIT's performance. They chose an input representation that maximized the VIT's strength, pre-trained visual features, and then pitted it against a less optimized image-based CNN. It feels like they built the track specifically for their car.
The biggest vulnerability, however, is the training data labeling process. The 136,878 recordings used to train the model weren't labeled by the 3 board-certified epileptologists. They were labeled by a trained NeuroPace employee using a clustering-based workflow.
Ah, the scalable shortcut. Instead of paying 3 experts for a year, they used 1 supervised employee and an algorithm to auto-label large chunks. That's a huge risk for label noise. If the clustering algorithm incorrectly grouped seizure and non-seizure clusters, that error was propagated to the entire 136,000 recording dataset.
The paper even acknowledges this in the error analysis. This discrepancy may, in part, be attributed to the clustering methodology. While clustering facilitated scalable labeling, it may have also introduced inconsistencies or label noise.
That explains the crucial difference. The 96.8% is on the soft test set, but the true, hard, expert-validated clinical dataset, 3,010 recordings labeled independently by 3 board-certified epileptologists, is where the accuracy drops to 95.8% for the subset with unanimous agreement.
That drop of a single percentage point is statistically significant evidence that the original training data contained a slightly softer ground truth than the expert-validated set. The model performed better on the data labeled by its own process than the data labeled by the gold standard.
It's a classic case of an algorithm being great at a task defined by a slightly flawed process. And then there's the generalization issue. Look at Figure 11. Testing the model on a different epilepsy type, the idiopathic generalized epilepsy, IGE dataset, caused performance to plummet to around 75% accuracy in F1 score.
That confirms the VIT, as currently trained, is a specialist, not a generalist. It learned the low-voltage fast activity and high-frequency patterns of focal epilepsy extremely well, as evidenced by the Figure 12 attention maps. IGE has a fundamentally different electrographic signature, generalized spike and wave discharges.
So the VIT is a brilliant diagnostician for one specific type of brain fire, but when you show it a different type of fire, it just shrugs and gives you a C-. The claim of generalizability is only partially met.
Overall, it's a breakthrough in VIT architecture application, demonstrating the power of visual pre-training on time-frequency data, but its stellar accuracy numbers should be viewed with a grain of salt, given the simplified baselines, the dependence on image input, and the inherent label noise introduced by the scalable clustering-assisted labeling process.
So, a phenomenal concept with an Achilles heel made of clustered and propagated errors. Data science, never a dull moment.
Okay, we have another prompt. I don't know, I think it's doing pretty well so far. I have to check a few things. It actually mentioned a NeuroPace employee. Yeah, that's highly unusual. Because they're mentioning all these experts, but they don't say what the employee, quotation marks, expertise. What's their expertise actually is. They're not mentioning that. That's a bit unusual. It's a bit unusual. Oh, right. Who would? Oh, okay. So, simple. Surely NeuroPace do have money to pay a board-certified epileptologist to review the data, which supposedly they did for some of the data, but not all of the data. Oh, this were labeled by a NeuroPace employee who was not a board-certified epileptologist but was trained and supervised by 3 senior NeuroPace colleagues, including 1 board-certified epileptologist. This is such a convoluted thing to do. Like you're publishing a paper like a big company. It is important when labeling the data, whatever, reviewing the data, to yes, be a board-certified epileptologist. But then, yeah, how does that work? Let's move on. Anyway, we have another review by the board. Or did we get to the bottom of it? We did training of models as well, and we actually had a even higher. Yeah, this one here. So same thing. We're looking at the spectrograms. Colored, no colored. I'm not sure if it mattered or not because we used the convolutional neural net. Eventually, the model was about 70 megabytes or so. So we have the results. The dataset is available in the public domain. You can go get it. This is a different dataset. It's not the Neuroset data. And we got to essentially even higher accuracy on this 600 images, seizure, non-seizure. So the seizure is what you see there. If that kind of shape. You can kind of see it there.
Yeah, so if you're new to keeping plants, try something like a snake plant or ZZ plant. They're pretty easy to take care of.
Manual tuning. That's the scientific euphemism for we babied the VIT until it worked perfectly on the specific dataset, but we treated the other models like they were rental cars. The VIT was clearly the favored child, benefiting from aggressive, targeted optimization that the baselines likely didn't receive.
And the parameter cog critique is even stronger when you consider the VIT49M variant.
Ah, the medium-sized sedan. Where is its performance on the main test set?
In Table 3, the VIT49M with color input achieved an average test accuracy of 96.0%. The VIT86M achieved 96.8%. Hold on, the 86M model is nearly 75% larger than the 49M model, yet the accuracy gain is less than 1 percentage point, 0.8%. That's the definition of over-engineering. The authors proved that the computational cost of the giant model is completely unjustified for the minimal performance benefit. They could have published a paper on the VIT49M and saved on cloud computing bills, but they wanted the highest number for the abstract.
It is a classic cost-benefit failure. The 49M model is the clinically viable option that they effectively sidelined. But let's remember the task itself. This is all about classification, seizure detection. It's retrospective. It tells the physician, a seizure happened here.
And that is a significant limitation on the model's ultimate clinical utility. The gold standard for epilepsy management isn't knowing what happened, it's knowing what's going to happen.
Exactly. The paper even admits it in the discussion. The question of whether there are signal patterns predictive of upcoming seizures, seizure forecasting, is an important area for future work. This VIT is excellent for cleaning up the data review backlog, but it's not an implantable alarm system to avert the next event. The title should be Using Vision Transformers for Electrographic Seizure Detection, which is still only a fraction of the problem.
And the real final test of scientific rigor, reproducibility. Is the data or the code available to anyone who wants to replicate this 96.8% miracle?
No. The data availability statement is the standard academic gatekeeper. It says, further inquiries can be directed to the corresponding author.
Translation, you get the text, we keep the secret sauce. There is no publicly available code repository, no link to the data splits, and certainly no mention of the precise manual tuning steps they used. Given the label noise from the clustering process, the simplified baselines, and the over-parameterized winning model, the inability to replicate this outside of NeuroPace's system is the single most critical flaw.
It's a fantastic proof of concept for the VIT architecture in neurophysiology, but the methodology leaves the door open wide for skepticism regarding the apples-to-apples comparison and the sheer cost of the winner.
Yeah, there's a few. Yeah, now that we know the details, yeah, so there's different VIT models with different types of, with different millions of parameter numbers. You have 49 color grayscale, didn't show any difference. And then you have the VIT 86 million parameters, which showed like a slight increase in difference in performance. So, yeah. I'm pretty sure if you fine-tune the ResNet 50 correctly, you could have get better results as well. So yeah, lots of questions. There's another main thing. Can you also by any chance determine the difference between figures 6, 7 and 8? The main concern is the y-axis, that we have actual scores percentage in figure 8, but you may have accuracy percentage in figure 7 and 6. Could you try and explain why that might be the case? And yes, the model is different, so we're using the 49 Yeah, the results don't... Yeah, I'm not sure if it actually... how does it compare to to table... I think it's 3. Yeah, how does it compare to table 3? Is there any issues, major issues there, or I'm just hallucinating? Yeah, over-engineering. Yeah, this table does suggest over-engineering. Considering you're doubling the number of parameters, but you're only marginally increasing the performance. That's yeah, that would be in the textbook, a definition for over-engineering. Let's do another one on figures 9, 10, 11, 12, because I didn't quite get what they are. So check it out. Thank you for subscribing. Every subscriber counts, well, literally, because we see the number. Everything we do eventually appears on the website. This is we're mainly focusing on simulations like this that actually doing something interesting or less interesting. Some of them don't fit the page. Can go check this tool, see how many vectors, what's the minimum number of vectors you need to replicate the image. So through 7 might be not enough. Would 11 be enough? Or get kind of something more artistic. 18? Yeah, 18 is more than enough. 18 is more than enough. And then you can see all the vectors working really hard to try and replicate the image as close as possible. And all the pre-calculation for each vector length is happening in real time as you draw. How good is that?
Misha, let's dissect the rest of the visual evidence. Figures 9, 10, 11, and 12 tell a story about where the VIT model is a genius and where it's a tourist.
Figure 9 shows the 4 confusion matrices, illustrating the model's performance when generalizing across different recording types: long episodes, magnet, saturation, and scheduled.
This is the VIT's triumph of generalizability. Remember, it was trained only on long episodes. Yet for scheduled and magnet, it showed a very clean bottom row. 0 false negatives.
Correct. Look at the scheduled matrix, bottom right. Of the 195 non-seizure recordings, it correctly classified 191 true negatives, row 0, column 0. More importantly, there are no false negatives. Row 1, column 0 is 0.
0 false negatives. That means for scheduled check-ins, the VIT is practically flawless at saying, this is a seizure and I see it. That's incredible for a system monitoring real-time patient safety because missing a seizure is far worse than a false alarm.
However, look at the long episodes matrix, top left. That has a higher number of both false positives and false negatives.
Why the higher error rate on the very data it was trained on?
Because long episodes are the most complex. They are initiated by the device's detection algorithms, meaning they often contain both seizure activity and non-seizure baseline, and can be noisy. The VIT is less perfect here because the data itself is the most diverse and ambiguous, reflecting true clinical reality.
Good point. Now, let's go to figure 10, the bar chart of recording durations.
Figure 10 shows that the vast majority of the clinical validation recordings were between 50 and 100 seconds long.
And Table 6 breaks this down. The VIT maintained high accuracy, 93.2% to 96.1% across all duration groups, whether the recording was less than 50s or more than 100s.
This is the crucial defense against the argument that the model only learned from a fixed length window. It proves the VAT is duration agnostic. The general pattern recognition holds whether the event is short or long.
Now for the big flop. Figure 11, generalization to IGE, idiopathic generalized epilepsy.
The bar chart speaks for itself. The accuracy drops from the mid-90s to the mid-70s. Against Expert 1, it's 75% accuracy and F1 scores.
This is the ultimate test of the VIT's training bias. It was trained on focal epilepsy, local, high-frequency brain fires. IGE has a completely different signature, generalized spike and wave discharges. The VIT's attention map is likely searching for its focal high-frequency signature and getting confused by the generalized lower-frequency patterns of IGE. It's an expert in one dialect of the brain, but completely lost in another.
The paper argues that 75% accuracy is still over 75% accuracy in F1 scores, suggesting it has some capacity to generalize. But in clinical terms, a 20-point drop in accuracy for a different population is a major finding that requires more focused training data.
And finally, Figure 12, the attention maps. This is the smoking gun of the VIT's internal logic.
The 3 seizure examples, left column, show the VIT focusing on a localized, high-frequency band, the top of the spectrogram, with nearly 1.0 probability.
That's the VIT confirming its bias. If it looks like a high-frequency smear of chaos, it's a seizure.
The 3 non-seizure examples, right column, show the opposite. The attention map is diffused, spread across all frequencies. The VIT is not seeing any localized hotspot.
It's a visual representation of its internal struggle. It's searching for the focal fire it was trained on. When it can't find it, it reports a non-seizure, with high confidence. This figure is the best part of the paper. It makes the black box white, but it simultaneously exposes the VIT's fundamental bias towards the patterns in its training data. A powerful tool, but one that only sees the world through the lens of a focal epileptologist.
Okay, that's figures 9, 11, 12. I think we might, yeah, so it's actually the attention maps will actually show you where the model was looking at. They didn't do any attention maps for the other models, did they? Yeah, their model, I think it just refers to the VIT 86 million parameters. And we'll do another review where we talk about parameter reduction, if there was any done or not. I suspect not.
Misha, let's play spot the statistical subterfuge with these y-axes. Look at Figure 6 and Figure 7. Their y-axis is clearly labeled accuracy percentage. Now look at Figure 8, the big final showdown. The y-axis changes to the much vaguer scores percentage. Why the switch?
That change is a matter of statistical necessity, and it highlights a major difference between the 2 datasets. Figures 6 and 7 are reporting results on the cross-validation test sets, the 113 patient data. This dataset was made class-balanced for training, Section 2.1, meaning the number of seizure and non-seizure examples were intentionally made equal. For a balanced set, accuracy is a perfectly fine metric.
But the main event, Figure 8, is the clinical validation dataset, the 241 expert-labeled patients.
Exactly. That dataset is not class-balanced. It reflects the natural, imbalanced distribution of seizures in a real-world patient. Table 2 shows this. For long episodes, you have 871 seizures, but 1,112 non-seizures. When you have class imbalance, a model can cheat by just predicting the majority class.
So if a model correctly guesses non-seizure 90% of the time, its accuracy looks great, but its ability to spot the critical 10% of seizures is terrible.
The solution is the F1 score. F1 balances precision, how often the model is correct when it says seizure, and recall, how many actual seizures the model finds. Because F1 is so vital when classes are skewed, the y-axis for Figure 8 must be labeled with the broader scores percentage to include both accuracy and F1 score. The model's real win is the 94.8% F1 score, not just the 95.8% accuracy.
So the shift in the y-axis is the paper quietly saying, the first two figures are lab work. This last figure is the real, messy, class-imbalanced world. The F1 score is the honest metric, and they made sure to lead with that.
Now, let's address your suspicion about the models, referencing Table 3. The results are internally consistent. Figure 6's mean accuracy for VIT 49M color is roughly 96.0%. Table 3 lists the mean accuracy for VIT 49M color as 96.0% plus or minus 0.6%.
No hallucinations. The math holds up. The performance of the 49M model is confirmed.
Which brings us back to the most critical point. The VIT 86M, the big winner in Figure 8 and Table 3, was the most heavily optimized. The sheer size difference and the minimal performance gain it offers over the VIT 49M strongly suggest a deliberate architecture choice.
It feels like they optimized two models, the small, efficient, and almost as good 49M model for practical deployment, and the huge, marginally better 86M model for the publication abstract. They're trading 37 million extra parameters for a mere 0.8% increase in accuracy. That's a classic case of academic performance inflation at the expense of clinical efficiency. They needed the highest possible number to make the VIT architecture look like the only option.
The paper's conclusion is sound. The VIT is superior to the CNNs they benchmarked, but the suspicion remains that if the CNNs were given comparable hyperparameter tuning and transfer learning, the performance gap would have been significantly smaller, making the VIT 49M the honest hero of the paper.
Yeah, so 49, considering like the almost half the parameters, would have been a much better model, considering it has very similar performance results. We'll do a summary and call it a day. Let me know if there's any questions, pop them in the chat. Any questions about this paper or the contents on the website?
Agreed. The study presents a powerful model, but its methodology has several vulnerabilities that weaken the strength of its core claims.
Summary of major critical issues in the VIT IEEG classification study. 1. Flawed benchmarking and over-parameterized winner. Unfair competition. The VIT 86M was pitted against significantly smaller and likely less optimized baseline models, ResNet 50 at 23M and 2D-CNN at 22M. This does not prove the VIT architecture is inherently superior, only that a heavily optimized, massively parameterized model outperforms simpler ones. The over-engineering trap. The size difference between the VIT 86M and the VIT 49M yielded a minimal
less than 1% accuracy increase, 96.8% versus 96.0%. This demonstrates that the 86M model is drastically over-parameterized and inefficient for the task, with the smaller model being the more clinically viable choice. The choice to lead with the 86M result is arguably an act of performance inflation for publication. Manual or favorite tuning. The baselines were given standard optimization, while the VIT-86M benefited from manual tuning, suggesting a deliberate, targeted optimization effort to achieve the highest possible score. 2. Compromised training data integrity. Label noise from clustering. The massive 136,878 recording training set was not labeled by board-certified epileptologists, but by a NeuroPace employee using a clustering-based workflow. The paper admits this process likely introduced label noise and inconsistencies into the training data. Soft versus hard ground truth. The model performed better on its own test set, labeled using the noisy clustering process, 96.8% accuracy, than on the independent, expert-labeled clinical dataset, 95.8% on the unanimous subset. This is evidence that the model learned the biases of the soft ground truth in the training data. 3. Limited generalizability and clinical scope. Classification, not prediction. The model performs seizure detection or classification, retrospective, a seizure happened, which is a valuable tool for review but falls short of the gold standard for patient safety. Seizure forecasting or prediction, prospective, a seizure is about to happen. The paper acknowledges this as a major area for future work. Failure on new populations. The dramatic performance drop from the mid-90s to around 75% accuracy when tested on the idiopathic generalized epilepsy dataset confirms the VIT is a specialist trained to recognize the focal, high-frequency patterns of the training data and struggles with other distinct epilepsy signatures like generalized spike and wave. 4. Reproducibility and interpretation concerns. Non-reproducible methodology. There is no publicly available code or data repository. The data availability statement directs inquiries to the authors. This lack of transparency, especially given the custom and potentially biased labeling and tuning steps, makes independent verification of the results impossible. Input dependence. The model's success is heavily tied to the initial step of converting the raw signal into a full-color time-frequency spectrogram, Figure 6, demonstrating a reliance on visual features learned from ImageNet rather than robustness to the raw spectral data itself.
In short, the paper is a landmark for applying VIT to IIEG, and the attention maps, Figure 12, are a brilliant piece of explainability. But the data prep, model selection, and final accuracy claim are all compromised by choices that prioritize a high published number over statistical rigor and cost efficiency.
A fantastic model, Misha, but a flawed experiment. It's like a joke with a brilliant punchline that requires a convoluted, heavily edited setup. It lands, but you have to ignore all the sweat equity.
Yazik, you have to see this website. It's called BioniChaos.
BioniChaos? Sounds like a band name for an electronica group where all the members are wearing lab coats and one of them plays a giant brain scanner.
It's a gold mine. It's a platform for biomedical data tools and simulations. I'm talking advanced EEG signal simulator, interactive MRI simulation.
Hold the phone. I'm scrolling. Wait. Right between Interactive Guide to EEG Technologies and the Deceived Brain and Interactive Illusion Viewer, there's the Penis Function Simulation Educational Tool.
Yes, the educational tool. A cornerstone of the curriculum, apparently.
Visualize processes like erection, urination, and ejaculation with real-time feedback. Misha, the data scientist, is this the kind of real-time feedback you're working with? Are you building a predictive model for chaotic erection events? Is there a confusion matrix for the prostate?
It's about anatomy and physiology, Yazik. It's scientific visualization. Just as the Hodgkin-Huxley action potential simulation models the neurons firing, this one models other firing. It democratizes complex biological processes. Look, let's talk about the serious chaos, the data visualization tools.
Fine. Serious chaos. Hit me with the heavy data, but I'm going to bookmark the penis function simulation as future stand-up material, ejaculation metrics.
Right. They have this great visualization called the Datasaurus Dozen visualization. It shows how 12 completely different, wildly patterned data sets can all have the exact same mean, standard deviation, and correlation.
Wait, you're saying I could have a data set that looks like a literal running dinosaur and another that looks like a scattershot blob, but statistically, they're identical? That's like me statistically being a well-adjusted person, but visually, I'm wearing mismatched socks and arguing with the traffic cone.
Exactly. It proves that if you rely only on summary statistics, you're missing the entire narrative of the data. You have to see the pattern. It's the whole philosophy of BioniChaos. The raw signal is everything.
So, the entire data science community learned the hard way that you can't trust an Excel spreadsheet until you visually confirm it's not secretly a T-Rex. That's a billion-dollar lesson.
It is. And then you have stuff like the Fourier series visualization. You can draw any complex shape, and the tool shows how it's recreated by a sum of rotating vectors, epicycles. It's the deep math of decomposition.
Epicycles. So complex reality is just a bunch of fancy circles chasing each other. That explains the lilac chaser illusion simulator. Is the lilac chaser just the universe's most efficient use of epicycles?
Fundamentally, yes. The site is a perfect reflection of its name. It's the beautiful, structured, bionic systems of the body presented with the interactive, slightly absurd chaos of the web. It's science that doesn't take itself too seriously, which is the only kind I trust.
I agree. Any scientist who's smart enough to build an advanced peristaltic pump simulation and then also thinks, you know what this site needs? A 3D model of a catheter is my kind of person. They understand that a little chaos is the key to engaging the messy human brain.
It keeps the data interesting. Now, if you'll excuse me, I'm going to run a PCA on the synthetic brain MRI generator.
And I'm going to adjust the back pressure effects on the peristaltic pump for science.
This page is the Advanced Peristaltic Pump Simulator. It lets you explore the workings of a peristaltic pump in real time. You can adjust parameters like the pump speed, number of rollers, tube diameter, occlusion, and back pressure to see how they affect the flow rate. This type of pump is used in many medical applications, such as in intravenous pumps for delivering medications, dialysis machines, and bioprocessing equipment. It's a great way to visualize and understand how these pumps work. So, how do you think different pump settings could impact medical treatments? Or what factors do you think are most important when designing a peristaltic pump for a specific medical need? How could this simulator help in research or training? What kind of experiments could you design using this simulator? It's a powerful tool for learning and exploration. The screen shows a penis function simulation. It displays a diagram of a penis and offers buttons to simulate various functions, such as arousal/erection, ejaculation, and urination. There is also a slider for adjusting the dysfunction level. How could we improve this simulation to be more accurate or informative?